So now we're going to learn a shortcut for finding the limit of rational functions as x approaches positive and negative infinity. Right, so if you see that your rational function has the same power in the numerator and the denominator, that means the limit of that function as x approaches infinity, it's just going to be the ratio of the coefficients. Right? So here they're both the same power. Both the numerator and denominator are first degree. So our limit is going to be 4 divided by 2 or 2. That's also, of course, going to be our horizontal asymptote. And so our horizontal asymptote is going to be y equals 2. Let's look at the next one. Right, so if the numerator is greater, has the greater degree, numerator has a degree of 2, denominator has a degree of 1, then the limit of our function, regardless of whether it approaches positive or negative infinity, in this case it's negative infinity, is going to equal infinity. Or, depending on your function, could be negative infinity. In this case it was infinity. Right? But it could be, you could also write does not exist. Right? Or it could be negative infinity, just not in this particular case. And if the numerator has the smaller degree and the denominator has the larger degree, then the limit of your function as x approaches, in this case it's infinity, is going to be 0. Right? And that's also going to be the horizontal asymptote. Right, so how about the following? What's the highest power in the numerator and denominator? Right, so remember that the square root of x squared is equal to x. Right, so they both have the same degree. We've got to be careful about taking the ratio of the coefficients. And let's take a look at that in the next page. There we go. So by the shortcut, the highest powers are the same. Right? We have the square root of x squared and x are the same degree. But be careful before dividing the coefficients. So notice that we're going to negative infinity. The numerator is going to be approaching negative infinity. Look how teeny tiny that is. I have no idea why that infinity sign is so teeny tiny. Right? And our denominator is always positive no matter what. Right? I'm not going to try and fix that, but there's a little tiny infinity sign there. I wrote it below as well. All right, so come on, get rid of the box. Denominator is always positive, no matter what. Come on. Oh, well. So that's going to be actually getting larger and larger and larger. It's technically heading to infinity, right, because it's always positive. I have no idea why my number is not appearing again. There we go. Oh, with a whole bunch of dots. Isn't that nice? Right, so since the denominator is always positive and the numerator is negative, we're not going to be headed to exactly the same thing. It's still going to be the ratio of the coefficients, but we have to be careful. Right, our limit, finally, we have to be careful with these pens. And how slow sometimes my board likes to write. As x approaches negative infinity is not going to be the ratio of the coefficients, it's going to be negative 1 times the ratio of the coefficients. So that's going to be negative 2. But that was a lot of work, just to simply write something down. Right? Now, you need to be able to not only know the shorthand here, you also need to be able to show the property. Right, so this is a little shorthand, however, it's not a justification. Right, so example, seeing limits as x approaches positive and negative infinity. Little reminder, so if a numerator and denominator are of the same degree, the limit is the ratio of the leading coefficients. If the numerator has a smaller degree, the limit is going to be 0. If the denominator has the smaller degree, it's going to be infinity or negative infinity, or it does not exist. Right? And so the justification, however, is our property. Right? So dividing by that highest power of x, right? Which, and the fact that our limit as x approaches infinity, positive or negative infinity, of 1 over x, or any constant over x to raise to any power, is always going to be 0. So let's practice this one using the property. Right? So we have the limit as x approaches infinity, and we're going to divide everybody by x cubed. So we have 5x cubed divided by x cubed, and then we have plus 11 divided by x cubed, all over 7x squared divided by, oops, this guy's just a little bit in the way. We go, no, they're all connected. No problem, no problem. We'll just move this over here. Otherwise, I have no space to divide. And for the most part, everybody moved. Oh, except for one little thing. There we go. All right, so 7x squared divided by x cubed plus x divided by x cubed minus 1 divided by x cubed. Right? And so that gives us the limit as x approaches infinity. 5x cubed divided by x cubed, that's 5, plus 11 divided by x cubed is just going to be 0. Oh, excuse me, we're not taking the limits quite yet. I'm sorry, we're simplifying, getting ahead of myself. 11x cubed, and then all over the, when we reduce there, that'll be 7 divided by x, plus, that'll be 1 divided by x squared, and that'll be 1 divided by x cubed, because that won't simplify at all. And now when we plug in, we've got 5 plus 0, and in the denominator, nothing but 0. All right, so in this case, the limit does not exist, right? And we don't have to really think, if we're not asked to really think about whether it's going to infinity or negative infinity, in this case, it's not really that important. So it's important on the other one, where we have a constant, and our limit exists, but whether we're approaching infinity or negative infinity doesn't really matter. So our limit of our function here as x approaches infinity just does not exist. And that's because, right, the numerator is growing much faster than the denominator. Right. In the next podcast, we're going to learn one more, not our last one for dealing with infinite limits, but one more, and that is multiplying by a conjugate. All right, so bye for now.